Enjoyed those graphing of that motion, and we're able to correctly match the motion with the graph that was shown. And if you find that you are struggling with that a little bit, please don't hesitate to contact me and let me know. But we're going to look more into the problem solving aspect of this as we go on, and we're going to try to throw a couple more things on this second screencast. I know it's a busy day, but we're going to build a strong foundation for everything we've got going on from here. So let's say that I see a graph like this. Okay, and a lot of things went on in this graph. Okay, this object sped up, I can tell that by this positive inflection. It slowed down, it stopped. That's what this zero slope would be here. The displacement's not changing. And then it started speeding up in the negative direction, reversed again. There's lots of things going on here, and it's kind of complicated to describe, but if I just wanted to know the average velocity over my entire trip, all I really need to concern myself with is the end point and the initial point. And the slope of that line is going to give me the average velocity. So it's simply going to be, what is this final delta x position, and what is this initial delta x position over time. And that's going to give me my velocity. Let's contrast that with instantaneous velocity. Okay, instantaneous velocity, I'm trying to identify at any given point what the velocity is at that time. So what we're going to do is find a line that is tangent to the slope at that point. And if it's tangent to it, it's only going to touch it in one single point. So let's say I were to draw a graph here. This would be an object that is speeding up over time. Okay, and I'm going to kind of draw a constantly increasing slope here. Okay, and if I wanted to find what the velocity was at any given point, it'd be the slope as that time approaches zero, as that change in time approaches zero. Let's say I wanted to determine what the velocity is right here. So I'll mark that with a little red dot. If I wanted to identify that as being what the velocity was at that point, what I'm going to try to do is draw a line that is tangent to that point that tries to correctly approximate the slope at that point. Now it looks like initially I may have gone a little bit too steep here, so I'm going to kind of click on this and maybe try to spin this down a little bit. What I'm going to try to do here is approximate this slope right at that juncture here. And I'm going to move this up, and the slope of this line then would be the instantaneous velocity for that displacement. And what you guys will do in calculus is you're going to determine the derivative, and that derivative of that will give you that value. But here we're going to rough it out a little bit more, and we're going to determine what the instantaneous velocity is graphically. So let's look at solving some problems. Given all these equations that we now have in our toolbox, just kind of like you can kind of do basically any home maintenance you have. If you've got a full toolbox, we now have a full toolbox of equations to help us solve a variety of problems here. So let's take a look at a couple. We'll start off easy and give a little bit more complicated one here, just to show that we can use a variety of these equations to solve these problems. So basically, they're word problems, okay? But if you go through the process and identify what you know and identify what you need to know, you'll solve these. So here we've got a car that's accelerating uniformly from rest to a speed of 20 meters per second in 12 seconds. We've got two questions for you. What distance is traveled, and what is the acceleration? So we are going to diagram this situation. We have an initial velocity of 0.0 meters per second here. We have a time of 12 seconds. And we know the final velocity is 20 meters per second. So these values right here actually end up being some of our givens. So diagram first, then you're going to write down what the problem is giving you. That's the G. Okay. My unknown, what is my delta x, how far did I go, and what was my acceleration? So I'm going to identify those are the two questions I've got right here. What distance is traveled, what was the acceleration? Those are the unknowns. But any problem will always give you enough pieces to solve the problem. Just like Hansel left enough breadcrumbs to find his way back home, there's going to be enough breadcrumbs here in your word problem to help get you where you need to be. So the equation we're going to need to solve for delta x, one equation we could use is simply V average delta t. That's equation from our toolbox, and we've written that before as 1/2 VI plus VF delta T. We have VI, we have VF, we have our time, so this should be smoother than a greased pig running downhill. Okay, we're going to substitute in. Our delta X is 1/2. My VI is 0. My VF is 20 meters per second. My time is 12 seconds. And so I'm going to substitute in, then I'm going to solve. Okay, so the distance that this car traveled was 60 meters. That was our first problem. Our second unknown was, what was the acceleration? The big thing is just identifying what equations you need to solve it. So one equation we could use is V final equals V initial plus acceleration times time. We have 3 out of the 4 variables here provided in our givens, and we just need to rearrange this in a way that helps us solve the problem. My initial velocity is 0, my final velocity is 20, my acceleration is 12 seconds. So what is the acceleration going to be? I'm going to end up taking 20 meters per second divided by 12 seconds, and that should give you, when it's all said and done, an acceleration of 1.67 meters per second squared. And that should be pretty good for us. Oops. Now this problem is a little bit more complicated. Okay, the whole idea is you got to choose the correct equation, and you got a lot of tools in your toolbox to work with. So let's say you've got a jet landing at 80 meters per second, and the pilot's going to apply the brakes 2 seconds after landing. The jet only has 500 meters of runway. What acceleration is needed to accomplish this, to slow this plane before it meets its demise here at the end of the runway, which wouldn't be good. Okay, so we're going to make sure that we take care of business and make sure that we break this plane in time. So when we diagram this situation out, we've got to identify first the fact that this plane doesn't start braking right off the bat. Okay, so we're going to draw the plane here. It's going to have coasted for 2 seconds before it even, you'll have to apologize for my drawings here. Let's make sure this plane can land here. So for these 2 seconds, this plane is going to be traveling at a constant velocity here. Okay, so for 2.00 seconds, it is going to be traveling. Whoops, we don't need that. It's going to be traveling at a velocity. So we'll put t. Let's switch the stylus here. So our time here, let's go like this, come on, is 2 seconds. And our velocity during this time is what they described up above here. It's this 80 meters per second. And then we want eventually this plane to stop right here. Again, this plane is looking like it's melting on the tarmac. Okay, so we've got a distance here. So we've got a delta x1, let's call this. Let's call this delta x2, during which time it's decelerating. I know that delta x1 plus delta x2 has to be less than or equal to 500 meters. Okay, that has to be my situation that I'm working with. So how are we going to? So all these would kind of fall into our land of what the problem is giving us. We diagram the problem. Our unknown is, what is delta x1? And we don't know that. We got to figure that out. What is delta x2 then? And then if I know those two, I should be able to figure out what my acceleration is needed to do that. Okay? So my equation that I'm going to be working with is going to say that my total delta x equals delta x1 plus delta x2. And that's the same as saying my velocity, my initial velocity, times that first time, plus I'm going to need an equation here that's going to help me figure out what this delta x2 is going to be. Now, I know that my initial velocity here, let's kind of chunk this into one here, is going to be, they don't give me a time for how long this is accelerating. So I need some variant of this equation. I'm going to need some variant of VF squared equals VI squared plus 2a delta x. So let's just worry about this delta x2. Let's kind of hold off on that a little bit. And let's solve for this right here. Let's kind of substitute in some values that we know here. So we're going to substitute in, let's call this delta x2. And we're going to take this over here and we're going to say delta x total minus my v initial times my initial 2 seconds of time here is going to equal delta x2. I'm going to reverse this a little bit. Delta x2 is going to equal, and I'm going to start substituting in what I know. I know my delta x total is going to be 500 meters, and I know that my initial velocity was 80 meters per second, and I know that the time it was doing that was 2.00 seconds, so that's the same as minus 160 meters. Notice meters per second times seconds. So what this says is that your delta x2 here, do a little color change there, delta x2 has to be in the neighborhood of 340 meters. Okay, that's good. So we now actually have a new given that we can work with. Okay, and let me get this. Okay, so this was actually delta x2. Okay, so that's my second accelerate or my second displacement. So what our unknown here and what the problem was ultimately looking for here was what acceleration was necessary for that to happen. Okay, and the equation we're going to need, since in all of our givens they didn't give us a time here for this section here, so we need to find an equation here that solves it without time. So the equation we're going to need, and I mentioned this earlier, that this is a valuable equation for us to have in our toolbox, is that if I have this value right here, now I can solve this without having my time. My VF final, we hope this plane stops, right? So that's going to be 0. And so I'm going to say that my VI squared here equals a negative 2a delta x, but I want to isolate acceleration by itself. So I'm going to say VI squared over a negative 2 delta x equals my acceleration. That's the equation. If you can get it to that point, guys, we are all gravy. So now we're going to substitute in. My acceleration is going to equal vi squared over negative 2a delta x. No, I'm sorry, negative 2 delta x, I should say. And I'm going to substitute in what I know. I meant to do that time. So my acceleration, my vi squared, remember it was traveling at 80 meters per second and it hadn't slowed down for the first 2 seconds. I'm going to take that 80 meters per second. I'm going to square that puppy, and a negative 2 times that second distance at delta x2 is 340 meters. And now I'm just kind of crunching some numbers here. Okay, so now I have my acceleration equals 6,400 meters squared per second squared over a negative 680 meters. Now that negative implies that it's a negative acceleration, which is what we want. We're slowing down. Okay, so that's going to be good. So let's see. So now when you do the final crunching, we're going to solve that problem. We're going to find what the solution is. That's my final S. My acceleration is going to end up being 9.41 meters per second squared, and it's going to be a negative 9.41 meters per second squared. Whenever you solve a problem, please box up your answer to the problem. That's what they're going to expect on the AP test. But you'll see here, the nice thing here is a meter squared over meter. That's why we end up with just meters in the numerator. This second squared flops down there. So that is going to be our answer.